Welcome to lecture B6. In this lecture, we're going to talk about the idea of a matrix norm. We'll also talk about the idea of a condition number for a matrix, and then finally we'll talk about the idea of ill-conditioning. Now there are a number of different matrix norms one could discuss or use in a problem, but for this lecture we're going to use a matrix norm that is also called the column sum norm. And the way that the column sum norm of a matrix A is calculated is the following. First of all, it's designated like this with the two vertical bars on either side of A. The two bars over A are just my way of designating that A is a matrix. And so to calculate the matrix norm of A, what we do is to use this formula here. Now, what does this formula mean? Well, the idea is that we're going to remember that Aij is the element in the ith row and jth column of the matrix A. So what this formula says is that we're going to pick a particular J, we're going to fix J, and then sum up the absolute values of all of the numbers in that column, in the jth column. We're going to add up the absolute values of all those numbers. And we'll do that for every column, for every J, and then we'll take the largest of those. Now, in case that's a little bit confusing, let's look at an example, and I think it will be immediately clear. So if we have A is equal to this 3 by 3 matrix, 1, -2, 3, -6, 5, -4, 7, -8, 9. Now let's add up the absolute values of the numbers in each column. If we add up the absolute values of the numbers in the first column, we get 1 and 6 is 7 plus 7, so we get 14. If we add up the absolute values of the numbers in the second column, we get 2. Remember, absolute values, so 2 and 5 is 7, and 8 is 15. And finally, if we add up the absolute values of the numbers in the third column, 3 and 4 is 7, and 9 is 16. And then finally, now that we have the three sums, we take the largest, and it's 16. So the norm of this matrix is 16. And it's just that simple to calculate the matrix norm using the column sum norm definition. Now to our next topic, the condition number of a matrix. Well, the condition number of a matrix is also very easy to calculate. And in fact, we're going to use what we just learned. The condition number of a matrix is designated as kappa of A, and it's equal to the norm of A times the norm of the inverse of A. So let's take, for instance, the matrix A, which is 1, 2, 3, 4. Well, in order to calculate the condition number of this, we would need the norm of A and also the norm of A inverse. So let's go ahead and calculate the norm of A. If we add up the numbers in the first column with the absolute values of the numbers in the first column, we get 4. If we add up the absolute values of the numbers in the second column, we get 6. 6 is bigger than 4, and therefore the norm of A is 6. Now, in order to calculate the norm of A inverse, of course, we need to calculate A inverse, and here is a brief review of how we do that using the Gauss-Jordan method. And I came up with this answer, -2, 1, 3/2, -1/2 for A inverse. And here I've checked it. Notice I used the A inverse that I calculated, and I'm multiplying it by A, and I do indeed get 1, 0, 0, 1. So this verifies that the matrix -2, 1, 3/2, -1/2 is indeed the inverse of A. And now let's calculate the magnitude of that. If we add up the absolute values of the numbers in the first column, we get 3.5. If we add up the absolute values of the numbers in the second column, we get 1.5, and 3.5 of this is, of course, bigger than 1.5, so 3.5 is the norm of A inverse. And now we can find the condition number of A. It's simply equal to the norm of A, which you remember was 6, times the norm of A inverse, which is 3.5, and so we obtain 21. Now finally, to explain the idea of ill conditioning, I'll use an example straight from your book. It's problem 20.4-20. And in that problem, we have the matrix A, which is 3, 1.7, 1.7, 1. And the two vectors B1, which is 4.7, 2.7, and B2, which is 4.7, 2.71. And what we're asked to do is to solve AX equals to B1, and also solve AX equals B2, and also to find the condition number of A. Now I'm going to do these tasks in the reverse order. What I mean is I'll find the condition number of A first, and then I'll solve AX equals B1 and AX equals B2. Now, to find the condition number of A, you remember we're going to need to find A inverse, and then we'll need to calculate the norm of A and the norm of A inverse. So here in these steps, I have calculated A inverse, and in this case it's rather tedious, so I'll just go ahead and skip right down to the answer that I've obtained, which is A inverse equals 9.09 repeating minus 15.45 repeating minus 15.45 repeating and 27.27 repeating. And I did check that right here. I took the value I calculated for A inverse and multiplied it by the given A, and we do indeed obtain the identity matrix. So this matrix here is correct. And then if you calculate the norm of A inverse, okay, let's add up the absolute values of the numbers in the first column, and we get 24.54 repeating. If we add up the absolute values of the numbers in the second column, we get 42.72 repeating. And since that is larger than 24.54, then we have that the norm of A inverse is 42.72 repeating. Now, to calculate the condition number of A, we also need the norm of A itself, but that's easy. Here is A. The sum of the absolute values of the numbers in the first column is 4.7. The sum of the absolute values of the numbers in the second column is 2.7. So we'll take norm of A is 4.7. And now we're ready to calculate the condition number of A. We have norm of A times norm of A inverse, which is 4.7 times this 42.72 repeating that we just calculated, and that would give us 200.81 repeating. So we end up with the condition number of A equals 200.82. Now this is a rather large condition number for such a small matrix. If A were maybe 10 by 10 or 20 by 20 matrix, 200 would not be such a large condition number, but for a 2 by 2 matrix, 200 is a rather large condition number, and this will have some consequences, as we will now see. Okay, so the rest of the problem was to solve the problem AX equals B1, and also to solve AX equals B2. Well, this is very easy now, because remember we have found the inverse of A right here, and so if we pre-multiply this equation by A inverse, we'll just get X on the left-hand side and A inverse B1 on the right-hand side. So we get X equals A inverse times B1. Or likewise for this one, if we pre-multiply both sides by A inverse, we get X equals A inverse B2. So if we calculate both of these, we will find that when we solve AX equals B1, the X is equal to simply the vector 1, 1. But if we solve AX equals B2, the solution to that is this: 0.8454 repeating, 1.27 repeating. Now, what is the significance of this? Well, remember, if we look here, B1 is 4.7, 2.7. B2 is 4.7, 2.71. So B1 and B2 are almost identically the same vector. They don't differ at all in their first component, and they differ by only 0.01 in the second component. And yet that very small difference between B1 and B2 leads to this large difference in the solutions when we solve AX equals B1 or AX equals B2. These two solutions don't look anything alike. And so this is the consequence of A having a large condition number, or large condition number. That's another way of saying large condition number. Let me write this. Large condition number that is another way of saying ill-conditioned. And this is to say that small changes in the right-hand side vector here can lead to large changes in the solution vector. And that's not a desirable situation in numerical problems. So this is something to be aware of. So that finishes the concepts for this lecture. And now let's look at some problems. Problem B 6.1. If A is equal to 2104, what is the norm of A? Choice A is 3, choice B is 4, choice C is 2, and choice D is 5. And problem B 6.2. If A is the same matrix 2104, what is the condition number of A? Choice A is 2, choice B is 2.5, choice C is 1, and choice D is 4. And this time we're going to have two problems in class, B 6.3 and B 6.4. And both of those will be given in class. So that concludes lecture B6, and good luck.